Hello learners, on behalf of Indira Gandhi National Open University, we welcome you for this lecture session. Today's topic is cogeneration plant. I am Subhasis Maji, professor in School of Engineering and Technology from Indira Gandhi National Open University. So dear learners, today's topic is cogeneration plant. Let us begin our discussion on the topic, that is cogeneration plant. After listening to this video lecture, you will be able to understand the concept of cogeneration plant. You will be able to appreciate the classification of cogeneration system, and you will be able to explain the types of cogeneration system. Let us begin our discussion on the topic, that is cogeneration plant, with the definition. Where a fuel source produce energy at the same time as producing thermal energy in one process, it is known as cogeneration process. So cogen, that means combined heat and power. In this process, the source of energy will be one, but the output will be combined heat and power. Power means the production of electricity and heat means thermal energy. Cogeneration or combined heat and power is defined as the sequential generation of two different forms of useful energy from a single primary energy source, typically mechanical energy and thermal energy. Mechanical energy may be used either to drive an alternator for producing electricity or rotating equipment such as motor, compressor, pump or fan for delivering various services. This is a schematic of cogeneration system with condensing steam turbine. You might have heard about the steam power plant, where there are four important components. One is boiler, which produces high pressure, high temperature steam by burning coal. The high pressure, high temperature steam enters into the turbine and the expansion of steam takes place in the turbine, thereby does work. And the shaft of the turbine which rotates coupled with the shaft of the generator which producing electricity. In general, the steam which is coming out from the steam turbine enters into the condenser and it condensed into liquid water, and there is a pump which transfers the water which is coming out from the condenser to the boiler, thereby complete the cycle. But here we are discussing about the cogeneration system. Now let us see how it operates. The boiler which produces high pressure, high temperature steam that enters into the steam turbine. Now during the expansion of the steam in the steam turbine, the steam is tapped from the turbine in between the process and it supplies to the process heater. So you see that is shown how the steam is tapped from the steam turbine during the process of expansion of steam inside the turbine, and that goes to the steam to process heater. The remaining steam further expands in the turbine and does work, and the turbine shaft rotates, thereby torque is generated in the turbine shaft. The shaft of the turbine is coupled to the shaft of the generator, which in turn producing electricity. Now the low pressure, low temperature steam which is coming out from the steam turbine enters into the condenser, thereby it is condensed into water and it is being sent to the condensate tank. But the steam which is sent to the process heater, it gives the heat for heating purpose for any process industries. After that, it will also be condensate and sent back to the condensate tank, and the pump after that sends the water which to the boiler, thereby completes the process. So, this is the process for cogeneration system. Now, we will discuss about the cogeneration system with closed cycle gas turbine. As you all know that in a gas turbine there is a compressor where air is being compressed. The high pressure air enters into the combustion chamber and the combustion process takes place in the combustion chamber, and the high pressure high temperature combustion gas then passes through the gas turbine, and the expansion of the gas takes place and the shaft of the turbine rotates, and the shaft of the turbine is coupled to the shaft of the generator, which ultimately producing electricity. After that, the gas which is coming out from the gas turbine enters into the heat exchanger, and in the heat exchanger the heat which is there along in the hot gases coming out from the gas turbine gives out to the fluid which is coming from the process industries. Actually, that fluid is being heated by the heat available within the hot gases coming out from the gas turbine. So, we are utilizing the heat which is there in the hot gases which is coming out from the gas turbine, and the hot fluid after taking heat from the hot gases sends back to the process industries for their processes. And at the outlet of the heat exchanger, the cold gases or air which is again sent back to the air compressor and complete the cycle. So, this is the cogeneration system with closed cycle gas turbine. Dear learners, we have discussed about the cogeneration process, the cogeneration method of power generation and supply to the end customer is wasteful, as only about a third of the primary energy fed into the power plant is actually made available to the user in the form of electricity. Now, this is the general process where the power is being generated with the conventional steam power plant. So, their efficiency obviously is very less, it is around 33 to 35%. In conventional power plant, efficiency is only 35% and remaining 65% of energy is lost. The overall efficiency of energy used in cogeneration mode can be as high as 85% and above in some cases. Now, let us take some example how the cogeneration benefits for the system. Now, let us take the conventional systems where heat is being or energy is being used for producing electricity, and also energy is being used for heating in the boiler for process industries separately. Now, let us take the example that energy available is 100 unit, and for the power station 60 unit is being utilized, and the efficiency of the power stations is 45%. So, 60 into 0.45, that is the output, that comes out to be 27 unit. So, out of 60 unit of energy which is given as an input to the power station, we are getting output in the form of electrical energy, that is 27. Now, the out of 100 unit we have already used 60 unit of energy for producing electricity, and the remaining 40 unit we are using for heating purpose in the boiler. So, that energy, if the boiler efficiency is 80%, so 40 into 0.8, that means 32 unit we are getting as a thermal energy out of 40 unit of available input energy. So, you see in this process, out of 100 unit of available energy, we are getting electrical energy, that is 27, heat energy, that is 32. So, 27 plus 32, that means 59 unit. How much is lost? 100 minus the total output, that is 59. 100 minus 59, that is 41. So, in this case the loss is 41 out of 100 units of available energy. If we use separately for generating electricity and for generating thermal energy. Now, if we take the combined heat and power plant, that is cogeneration plant, whose efficiency is around 84%, then if the available input energy is 70, then 70 multiplied by 0.84, that comes out to be 59 unit as an output. Out of 59, 27 is used for electrical energy and 32 unit of energy is used for thermal energy. So, the output is same as in the previous case, but in this case the out of 70 unit of available input energy, output energy we are getting 59 unit of energy. That means the loss is only 70 unit, but in the previous case the loss was 49 unit of energy. So, obviously the combined heat and power plant is beneficial. Now, whatever we have discussed, so I am repeating that discussion, that like let us consider one example. Suppose a chemical industry requires 27 unit of electrical energy and 32 units of heat energy. The primary energy input in power plant will be 60 unit, that we have discussed earlier. So, output is 27. So, in this case, that if the 60 unit is the input energy for the power plant and power plant efficiency is 45%. So, output will be 60 multiplied by 0.45, that comes out to be 27. That is our required electrical energy. If a separate boiler is used for steam generation, then the fuel input to boiler will be 40 unit, because the boiler efficiency is 80%. So, 40 multiplied by 0.8 comes out to be 32. Now, if the plant had cogeneration, then the fuel input will be only 70 units, that is 27 plus 32 is the output from the 70 unit of available energy for the cogeneration plant. So, if the cogeneration plant efficiency is 84% and the input for the cogeneration plant is 70, so output will be 70 multiplied by 0.84, that comes out to be 59. Out of 59 unit of energy, 27 is utilized for the electrical energy and 32 unit for thermal energy. The total loss, which was 41 units in case of separate heat and power inputs, has now reduced to 11 units in cogeneration mode. Along with the shaving of fossil fuel, cogeneration also facilitates reduction in the emission of greenhouse gases, particularly carbon dioxide emission. Cogeneration systems are normally classified according to the sequence of energy use and the operating schemes adopted. Classification of cogeneration systems like topping cycle cogeneration system and bottoming cycle cogeneration system. Now, see the diagram. The topping cycle system, that there is input as fuel and prime mover and the power generation unit, and we are getting electricity as an output. But for the topping cycle, our main important thing is to generate first electricity. After that, we will use the waste heat for the heating purpose. Like the system which we have already discussed. So, in the heat recuperator, we can extract the heat from the steam which is coming out from the turbine. That heat we can use in process industries. So, here this system is known as the topping cycle, because heat we are getting as a byproduct, but our main important aspect is to generate electricity. Bottoming cycle is our main important thing is to generate thermal energy. Say for example, we are considering a boiler, and boiler is generating say heat by burning of coal inside the boiler, and obviously the fuel which you use in the boiler may be coal or oil or natural gas. So, thermal energy is required, we are getting as an output from the boiler, that is used in the process industries. But the boiler, the flue gases which comes from the boiler as an output or waste, is that waste heat is recovered through heat recovery boiler, and that heat is being utilized for generating steam, and that steam may pass through the steam turbine, and thereby in the generator we can produce electricity. So, in this case our main important point is this, that here mainly we are getting the thermal energy from the boiler, and that is our main important part for the process, because in some industries like chemical industries, cement industries, huge thermal energy is required. But the waste heat we are tapping from the boiler flue gases, and that heat can be utilized for generating steam in the heat recovery boiler, and that heat can be utilized for converting water into steam, and that steam we can utilize for generating electrical energy. In a topping cycle, the fuel supplied is used to first produce power, and then thermal energy which is the byproduct of the cycle and is used to satisfy process heat or other thermal requirements. In a bottoming cycle, the primary fuel produces high temperature thermal energy, and the heat rejected from the process is used to generate power through a recovery boiler and a turbine generator. Typical areas of applications include cement, steel, ceramic, gas and petrochemical industries. Topping cycle cogeneration is widely used and is the more popular method of cogeneration. The two types of steam turbines mostly widely used are back pressure and extraction condensing. The choice between back pressure turbine and extraction condensing turbine is driven mainly by the quantity of power and heat, quality of heat and economic factor. The extraction points of steam from the turbine could be more than one depending on the temperature levels of heat required by the process. Now, why we will go for extraction process? Because sometimes the high thermal energy is required. So, in that case we have to tap the steam as per the requirement of heat for the process industries. So, we have to extract heat from the turbine at a particular point which actually supplies the heat or thermal energy as per our requirement. So, as per our requirement we have to extract the steam from different points of the turbine in the case of extraction condensing process. The main advantage of using steam turbine over other prime movers is the option of using a wide variety of conventional as well as alternative fuels such as coal, natural gas, fuel oil and biomass. The power generation efficiency of the cycle may be sacrificed to some extent in order to optimize heat supply. Now, this is the simple back pressure. So, in this case the boiler is there which generates high pressure high temperature steam. That high pressure high temperature steam enters into the turbine at point 1. So, here the number is given, entry point of the steam is in the turbine is point 1 and point 2 is the exit point of the low pressure low temperature steam, and at the point 2 it is entering into the process heater, and point 3 is the exit point of the process heater, which is also the entry point of the pump, and point 4 is the exit point of the pump and entry point of the boiler. So, now we will calculate with the help of simple equations how much heat we have recovered in the process heater, how much heat we are, how much work we are getting from the turbine as an output. Now, let us see how we can calculate the simple say heat recovery for this simple back pressure cogeneration plant. In this process, we have taken the diagrams of TS diagram. This is a very simple diagram, temperature entropy diagram. As I already told you that point 1 is the entry point of the turbine and point 2 is the exit point of the turbine. Here you see that the steam is leaving from the turbine as a saturated vapor, and the process heater is the process in between 2 to 3 and 3 to 4 is the pump work, and the heat input in the boiler is from point 4 to point 1. Now, WT is the turbine output in kilowatt, that is kilojoule per second, and QH, that is process heat required in the process heater, that is kilojoule per hour. So, W is the steam flow rate in kilojoule per hour. Now, we can write that WT into 3600 is equal to W into H1 minus H2. Now, turbine work is from 1 to 2 and H1 is the enthalpy at the beginning of the process in the turbine, and H2 is the enthalpy at the exit point of the turbine. So, W into H1 minus H2, that is the work done by the turbine. So, it is equal to WT multiplied by 3600. Why we have multiplied by 3600? Because WT is in terms of kilowatt, we have to convert into kilojoule per hour. Now, the heat recovery, that is in the process heater, is H2 minus H3 multiplied by the W is equal to QH. Now, QH, that is from the previous equation you can see that QH is equal to W into H2 minus H3. So, W is equal to QH divided by H2 minus H3, put the value of W in the first equation, then you see how we can get the heat recovery in the process heater, that is QH. So, WT multiplied by 3600, put the value of W, small w, that is the steam flow of steam per hour, that is QH divided by H2 minus H3 multiplied by H1 minus H2. So, from this equation we can get the expression for QH, that is the heat recovered in the process heater, otherwise it would have been lost in the condenser. So, QH is equal to WT multiplied by 3600 multiplied by H2 minus H3 whole divided by H1 minus H2. But the fraction of energy Q1, that is the heat input in the whole process utilized in the form of WT and the process heat QH in the cogeneration power cycle is equal to, that is WT plus QH whole divided by Q1. In the cogeneration power plant, the condenser loss is 0 and the fraction of energy utilized is maximum. The efficiency of a back pressure steam turbine cogeneration system is the highest in cases where 100% back pressure exhaust steam is used, and only in efficiencies are gear drive and electric generator losses and the inefficiency of steam generator. Therefore, with an efficient boiler, the overall thermal efficiency of the system could be as high as 90%. So, this is the extraction condensing steam turbine, and you see that boiler which generates steam and the high pressure steam enters into the turbine, and the steam is extracted from the steam turbine at a particular point as per our requirement, and that heat is recovered in the process heater, and after that when it is condensed through the pump, again it is sent to the boiler, and the remaining steam will be further expand in the turbine, and after that the low pressure low temperature steam passes through the condenser and it will be condensed into water, and pump 2 is there to send that water back to the boiler to complete the process. In this type, the steam entering at high or medium pressure is extracted at an intermediate pressure in the turbine for process use, while the remaining steam continues to expand and condenses in a surface condenser. In a two-stage extraction condensing turbine, medium pressure steam and low pressure steam pass out to meet the process needs. In an extraction condensing steam turbine system, the steam for the thermal load is obtained through extraction from one or more intermediate stages at appropriate pressure and temperature. The remaining steam is expanded in the turbine. This is the gas turbine cogeneration system. In this case, the gas turbine air is entered in the compressor, and in the compressor the air is compressed to a high pressure. After that, it is entered into the combustion chamber. Fuel is injected to the combustion chamber. In the combustion chamber, the combustion of air along with the fuel takes place, and the high pressure, high temperature, the combustion gases enters into the turbine, and turbine actually operates the generator for producing electricity. But the fraction of output from the turbine is used to operate the compressor. But the flue gas which is coming out from the turbine, and that is again the heat is being recovered at heat recovery system, and that heat we can use for the process heater. Gas turbine cogeneration system can produce all or a part of the energy requirement of the site, and the energy released at high temperature in the exhaust stack can be recovered for various heating and cooling applications. Though natural gas is most commonly used, other fuels such as light fuel oil or diesel can also be employed. The typical range of gas turbine varies from a fraction of megawatt to around 100 megawatt. Gas turbine cogeneration has probably experienced the most rapid development in the recent years due to the greater availability of natural gas, rapid progress in the technology, significant reductions in installation cost, and better environmental performance. Gas turbine has a short startup time and provides the flexibility of intermittent operations. Now we have discussed in detail about the cogeneration system. Let us very quickly discuss what we have shared with you. We have discussed the concept of cogeneration plant. We have also discussed the classification of cogeneration system, and lastly we discussed about the types of cogeneration system. Here we conclude our discussions. Thank you.